Hello everyone, welcome to the 27th episode of this series. In this video, we'll learn how to compute a basis for different types of subspaces. So last time we learned about basis and dimension. More explicitly, we learned that a basis for a subspace V is a linearly independent spanning set. And we also learned that bases are not unique, but anytime you have two different bases for a subspace, they're going to have the same number of vectors. And this number uh, is called the dimension of the subspace V. So as I mentioned a moment ago, in this episode, we are going to learn how to quickly find a basis for different types of subspaces and therefore compute their dimension. So note that every spanning set for a subspace V contains a basis for V. And that is because every basis is a linearly independent spanning set. So in general, a spanning set might not be linearly independent, and that's what stops it from being a basis. But we can fix that by throwing out enough elements. For example, this first set with four vectors is a spanning set for R2, but since there are too many vectors, this is not going to be linearly independent and therefore not a basis. So we can carefully throw out two vectors so that the set is only of size 2 or has two elements. And if it still spans R2, then it's going to be a basis. And this tells us that any spanning set for a subspace V must have at least a dimension of V many vectors. So this idea of throwing out vector works, but it's kind of slow. So here's an algorithm to find a basis from a spanning set. So what we do is we take our spanning set. So let's say there are k vectors that span this subspace V. We concatenate them to form a matrix A. We use row operations to put this matrix A into a row echelon form and call it B. We check which columns of B contain a leading one. And then we keep the vectors in the original set corresponding to only those columns which have a leading one in B. And the resultant set of vectors is a basis for the space V. Let's demonstrate that using an exercise. So we are given that our subspace V is a span of these three vectors. We have to find a basis for V. So we can take the spanning set that we have and we can concatenate all the vectors to form this concatenation matrix. Then we can put it into REF and we get this matrix with columns 1, 0, 0, 2, 1, 0, and 3, 2, 0. So there are only two columns that have a leading one in it, the first two columns. So we take the vectors corresponding to the first two columns. So, the vector corresponding to the first column is 147 and corresponding to the second one is 258. So we just take those two vectors from the spanning set and this gives us our basis for subspace V. Okay, so recall that the span of a given set of vectors is the same as the image space of the concatenation of those vectors. So we can use this fact to reformulate the last argument. In other words, if we have a matrix A, one basis for the image space of A is just given by the columns of A in which an REF of A contains a leading one. So we're just exploiting what we learned on the previous slide to get ourselves a way to find basis for the image space of A. And of course, you have to remember that there are going to be more than one bases for the image space of A like any other subspace. So let's look at an exercise. So we're given this 4x4 matrix and we want to find a basis for the image space of M. So just use the algorithm that we saw a moment ago. So we saw that a basis for the image space of M is the same as the basis of the subspace spanned by its column vectors. So we first turn it into a matrix in row echelon form, and we see that there are only two columns that have a leading one. So we just take those columns, and those are going to form the basis for the image space of M. So corresponding to the first column, we have 1, 1, 1, 1, and column corresponding to the second one, we have 1, 2, 3, 4. So that forms the basis for the image space of M. So note that this algorithm tells us how to produce one basis for the image space of A. The number of vectors in this basis is directly given by the number of leading ones in a row echelon form of A, and that just by definition is the rank of A. But we also know that the number of vectors in any basis for the image space of A will just be the dimension of the image space of A. And using these two, we get to an alternative definition of the dimension of the image space of matrix A. So, as one would suspect, the dimension of the image space of A is the same as the rank of the matrix A. So in the above algorithm, we started with a spanning set, and then we construct a basis that is contained in this S. So we just throw some elements out essentially. On the other hand, it's important to note that every linearly independent subset of V is contained in some basis for V. So the idea is that we can start with a linearly independent set, and if it's not already a basis, that is, if it doesn't span the subspace already, we construct a basis by adding vectors which do not disrupt the linear independence, and that would turn the set into a basis. So, for example, we start, with a linear independent set, with 2, 3 vectors, so 1, 0, 0, and 1, 1, 1, and then we can turn it into a basis by adding another 3-dimensional vector, such that the collection of these vectors now span the entire R3, but the linear independence is not destroyed. So this idea of constructing a basis from a linearly independent set kind of moves in the opposite direction compared to the first algorithm, because instead of throwing elements out, we are carefully adding elements in. The problem is that we don't have any general algorithm for this, but it is still a useful fact. So because every linearly independent set of V is contained in some basis of V, we get the following fact that any linearly independent set in a subspace V has at most dimension of V many vectors. Okay, so let's look at an example. So because the dimension of R3 is 3, this set of vectors in R3 is not going to be linearly independent because 4 is bigger than 3. And this brings me to another fact, and that is that any subspace of Rn must have dimension at most n. And why is this true? This is true because any basis for a subspace of Rn is going to be linearly independent in Rn as well. It may not be basis for Rn, but it's going to be linearly independent in Rn. But because Rn can have at most n linearly independent vectors, that means the basis for a subspace in Rn can have at most n elements, and that tells us that the dimension of the subspace can be at most n. So this brings me to another special bound. So this is just an equation that summarizes what we've seen so far, that the number of vectors in a linearly independent set in a subspace is going to be less than or equal to the dimension of the subspace, and the dimension of the subspace is going to be less than or equal to the number of vectors in a spanning set for V. So if these inequalities actually happen to be equalities, that is, if you have a linearly independent set which has dimension V many vectors in it, or a spanning set that has dimension V many vectors in it, then we can make some stronger claims. So if a spanning set for V has dimension V many vectors, recall that this is the smallest possible size for a spanning set, then it has to be a basis. Similarly, if a linearly independent subset of V has dimension V many vectors, which is the largest possible size for a linearly independent subset, then it also must be a basis. So for example, if my subspace V has dimension 3, then any spanning set for V which has 3 vectors in it is also going to be a basis. And similarly, any linearly independent subset of V which has 3 vectors is also going to be a basis. Now, we can restate the theorem in the following way. We'll call it 2 out of 3 rule for checking a basis. So let's say we have k vectors in a subspace V, V1 through Vk. If any 2 of the following 3 properties are true, then the third one is automatically true as well. So the 3 properties are that V1 through Vk is a spanning set, V1 through Vk is linearly independent, and that the dimension of V is k. So if any 2 of these are true, then the third one is true as well, and as a result, these collection of vectors even through Vk forms a basis for the subspace V. So if you know the dimension of your subspace V, and you want to check if a chosen subset S is a basis, first ask yourselves, like what are the number of vectors that are present in S. If it's the wrong number of vectors, then it's clearly not a basis. And if it has the right number of vectors, then you already have one condition out of the 3. So you only need to check one of the other 2 conditions, and typically one of them is going to be easier. Okay. With this, I would like to end this episode. Hopefully things make sense. I will see you guys soon. Up until then, happy learning.